Can you guys hear me? Thanks, Martin, for the introduction. So as Martin said, like my group is more known for its lightweight formal methods work. So today, for a change, I'm going to talk about like the performance work. So as Martin told me, I have a weird trajectory, right? So I was advised by a computer architect who is enamored by formal methods and dabbles in like a lot of formal verification. So why performance? And like everyone knows, like a lot of people have been making a lot of talks about performance, and like performance is important. As there was a talk today, we talked about like a lot of when you search Stack Overflow, how do I get performance in large-scale systems? And in this talk, I'm going to talk about how do you get performance on a single node, but you can also extrapolate it to distributed systems with lots of other nodes. And the talk is about parallel programming. So when I talk about parallel programming, the general perception is, man, it's really hard. And if you guys have not seen it, there's a fantastic book on arXiv by Paul McKinney, who is one of the designers of the RCU data structure. The title of the book is Parallel Programming Hard? If so, what can we do about it? Writing parallel code requires a different mindset. And there's a fantastic quote which talks about like, oh, first of all, you need to get programs correct, and then you need to think about performance too. And it talks about some of the emotional scares, like gray hairs, and a lot of time that is lost in this exercise. There's a lot of truth in it, like a lot of people spend a lot of time thinking about performance and correctness in these issues. And some of these issues can be alleviated. And this is what the focus of my group has been. And one of the philosophies of my group is when you say parallel programming to a lot of people, they think about it in the wrong abstraction. Like when I say parallel, they start thinking about threads. So if I ask you to write a program today, like let's say I ask you to write quicksort, do you go and start writing in assembly? No, you use abstractions, right? So most people use the wrong abstraction, and which makes the problem even more harder. So lack of use of wrong abstraction, lack of like good analysis tools and performance tools. This has been the root cause of this notion that parallel programming is pretty hard. And long time ago, when I was just a new faculty member, I had the opportunity to teach a parallel programming class. And I will use this as an illustration to illustrate some of the misconceptions that people have when they start parallel programming. I gave them a very simple exercise, right? So you have a range of numbers, some range 0 to n, and I want you to find all primes in this range and do some computation f, like f is a heavyweight computation. Let's say square root of all the primes that you found, and output me the result. And I wanted them to write a parallel program. This is a data parallel program, right? Like if you have taken parallel programming course, like this is embarrassingly parallel. And what do my students do? When I told them to write a parallel program, okay, the first thing that came to their mind is, oh, I should start using threads. Okay, what should I use? Stack Overflow, pthread. Okay, pthread create. Started doing this. And man, like writing a lot of code is a recipe for a lot of bugs, so minimize your amount of code. So one of the things I advocated was there is a parallel programming model called OpenMP, where you just add pragmas to your code, and you incrementally add parallelism. And if you don't know OpenMP, it's pretty feature-rich. You can quickly add parallelism to your code. There is like you can get like SIMD parallelism using vector instructions in your code. You can use tasks, you can leverage multi-cores, and it seamlessly integrates with MPI, so you can scale your application. So the key thing to take away is like you write some pragmas like this, your code runs in parallel, it gives you performance. And for like in people who are getting started with parallel programming, this might be a good segue to the parallel world. So I introduced them, and then I taught them basic concepts of parallel programming. And what do you do for the problem? The first thing of the rule 101 of parallel programming, you have to do geometric decomposition. You have a range, you have to do it in parallel, split the range into n parts, right? If you have 4 cores, split it into 4 parts. And this is what my students did. So they had 4 cores in the machine. Take the range, split it into 4 parts, give it to 4 cores on your system, run the primes. What speed up do you expect? It's not 0. You get like some speed up. It was like in this case, it was 80% speed up over your serial execution. And most of you have taken parallel programming courses or know about it. What's the reason? Anyone? Amdahl's law, right? Load imbalance. So checking a number, 997,997 is prime, is much, much more expensive than checking 42 is prime, right? So, and you are bottlenecked by the serial part that has to, the longest part that has to execute serially. And this is where, like, I make an advocacy for task parallelism. I'm not the first one. Like, there are a lot of people who have made this case. So rather than thinking in terms of threads, think in terms of tasks. And then delegate this to the runtime. So, and you can use work scaling or other scheduling algorithms that have been proposed in the literature. The tasks get mapped to the underlying threads. You have scalable performance. And going back to the example that I have, what is the how does it map to tasks? Like checking a single number is a prime is a task. And then you just say, like, you recursively create tasks and give it to an underlying system. And in this case, my students were able to get like 3.8x speed up on 4 cores. So the lesson to take away here is, like, use the right abstraction. In this case, like, for this problem, tasking was the right abstraction. So if you thought about the right abstraction, the problem becomes a bit more easier. The second message I want you to take away from this is, like, there's a need for performance portable code. Like, you got reasonable performance, 3.8x on 4 cores, right? Is it good? So when we write programs, we don't write programs that works just for a single input, right? It works for large classes of inputs. So when we write a parallel program, it should work on a large class of machines with varying core counts, varying parallelism models. So is this program performance portable? What do I mean by performance portable? So if I run this on a 100 core machine, am I going to get like close to 100x speed up? It's called scalability in the parallel programming community, or you can call it by any other name. So you want your code to be reasonable. As a programmer, you want to write once and use it on a different set of settings. And I wanted my students to learn about performance portability and write scalable code. So I asked them to use a wide variety of profilers that are available. And this community, there are a lot of profilers out there. Okay? And in fact, what turned out was, like, when my students tried to debug, like, they got like 3x on 16 core machine, they used some of the profilers. Like, most students would use gprof, and it would say, like, oh, the prime function is spending a lot of time. And they would optimize it, and then the program would slow down. So the key message is these profilers are all useful, but most of them just tell you where your program spends its time. That may not be a good indicator of where you should focus on. And then what limits scalability? Something that executes on the critical path, right? Some of these tools do provide information about the critical path. What is the largest serial part that has longest sequence of instructions or blocks that have to be executed serially? But if I address this, will it improve? So most people spend a lot of time in parallelizing their code and eventually realize they don't get any speed up at all. So there's a fantastic line of work recently from Charlie Kurtzinger and Emery's group called CAUSE. What does it do? It predicts if optimizing a single line of code improves the speed up or not, which is fantastic. Like, for example, you have a memcached server and you know you want to optimize a single line. Does it matter? Like, it gives you it has sophisticated statistical analysis to figure out, oh, does it predict speed up? It was a good tool. I gave it to my students in the later iteration of the course. For some regions, they could use it to predict speed up, but it did not say anything about scalability. And especially, and I made an advocacy for task parallelism. With task parallelism, the runtime itself is doing load balancing, and it was confusing the statistical analysis in the CAUSE tool, and they were misguided again. And one of the tools that we found really useful was Intel, in its latest release, has Intel Thread Advisor, which tries to predict speed up. So you need to choose the region where you want to parallelize, and Intel predicts, the Thread Advisor predicts what the speed up would be. This was pretty useful. But if you have a million-line code base, where do you go ahead and like put these annotations to predict like improvements in speed up? So identifying where to look has an observer bias, right? It's a needle in a haystack. Like, you have to now search for a lot of things. And this is like the motivation for our work. Can we build a profiler and an advisor that can pinpoint these are the regions that you need to focus on to improve scalability in your program. And this is the motivation for the entire work. And let me make, for people who want to have something to take away from the talk, this is a takeaway slide. And these are the 3 points that I want to take away. One, we make a case for measuring logical parallelism in the program. So what is logical parallelism? Let's say I give you an infinite number of cores and an ideal runtime. What is the maximum speedup that you're going to get? If you take a computer architecture course, this is like a limit study done, right? So I give you an ideal runtime, infinite number of resources. What is the highest speedup that you're going to get? So what is it constrained by? This is constrained by the program semantics and the serialization that is inherent in the program's execution for a given input. So we make a case for measuring logical parallelism. Unfortunately, to our surprise, we didn't see many people actually computing logical parallelism. And to compute logical parallelism, what do you need to do? So you need to identify in the dynamic execution, you can visualize it as a trace. There are some fragments that have to execute serially, some fragments that execute parallel according to program semantics. You need to capture this logical series parallel relations. And then measure what is the work that is actually computed in each fragment. And effectively what we do is we build logical series parallel relationships and perform fine-grained measurements. And what we make a case for is this logical series parallel relationship plus fine-grained performance measurements is a performance model with respect to logical parallelism, computing logical parallelism. And you can use this to estimate what regions matter and what doesn't matter. You had a question?
Yeah, I had a quick question. So this kind of logical parallelism, like span depth kind of thing, this is like what, I think Silk had such tools, right?
Yeah, sure, Silk Prof.
But I guess maybe not the second part with the measurements.
So again, we can get into the details, just hold on. And yeah, so people have done it. Silk Prof is fantastic, but if you have to run your program serially, running a large scalable program serially is a performance limitation. So again, we'll get to the details in a few minutes. So the first thing I want you to take away is measure logical parallelism, and to measure logical parallelism, compute logical series parallel relationships and do for fine-grained measurements. And then where should the programmer focus on? Regions with low parallelism and the critical path. So this is the profiler part of our tool. And now we want to give information to the user what matters in increasing parallelization. And this is where the what-if analysis comes in. If you want to identify if something matters, you need to have a performance model, right? So, and this logical series parallel relationship plus fine-grained measurement is a performance model. Now, we identify what matters by performing what-if analysis on this performance model. What is what-if analysis? Our what-if analysis mimic the act of parallelization. So you want to estimate what matter. So you take a region. If I parallelize this, what happens to the total parallelism in the program? And what happens when you do parallelization? Your total work is exactly the same. Your serial work gets reduced. So our what-if analysis mimic the act of parallelization. And with our what-if analysis, we identify a set of regions that you need to parallelize to increase the parallelism to some threshold that you want. And our goal was to improve the parallelism and the speed up of your program. To improve your parallelism, you need to reduce serialization. And your program may be serialized at multiple places. Our what-if analysis identify all these regions where you have to parallelize to improve logical parallelism. The second thing that you encounter when you actually write a parallel program and run it is you have secondary effects of execution. So what are secondary effects? Here, your program is running contended for a hardware resource. So what we realize is you can use this performance model and perform differential analysis. Construct a performance model, which is logical series parallel relationship plus fine-grained measurements for a parallel execution, and one for an Oracle execution. Let's say Oracle is an ideal execution. How do you construct it? There are various ways depending on what you're looking at. And then do a fine-grained differencing of it. And what happens when you have secondary effects? There'll be inflation in some metric of interest. In this case, there'll be inflation in work. And now you can localize, these are the regions that you need to focus to address secondary effects. So this is a takeaway slide, and this is the advisor part of our profiler. Yeah, a profiler consists of two parts. A profiler which says what are the things that I have low parallelization, Amdahl's law, this is causing serialization. The second part is what are the things that you need to address to improve parallelism in your program. And the key thing that you need to do is you need to compute logical series parallel relationship, and you need to do fine-grained measurements. And now this is what I'm going to illustrate. Okay, and what we have shown in the last few years is this abstraction is pretty general for multiple programming models. We have done this for Intel TVB, we have done this for OpenMP. In this talk, I'll focus on OpenMP. I'll also teach you a bit about OpenMP if you don't know OpenMP. Okay. So as Martin was highlighting, like Silprof guys were measuring logical parallelism too. So what is the idea behind computing logical parallelism? You want to execute your program or profile your program on a machine with low core count and identify if you execute it on a machine with higher core count, will it have scalable speedup? Okay? To do this, we have to identify what fragments of your program execute in series according to the program semantics. As Martin was highlighting, there are various data structures that people have proposed. One is the SP parse tree, which is a data structure that captures series parallel relationship, and Martin was involved in other work called dynamic program structure tree that occurred at PLDI 2012. So we want to construct such a data structure for an OpenMP execution. And if you have a structured parallel programming model, it's easy to construct, and then you should be careful in constructing the semantics. So for example, what are the issues that can happen? You have a parallel program, you execute it, and you see the execution. You're running it on a 2-core machine, you can see what parts actually get serialized. On a 2-core machine, what parts executed on a parallel. Now you want to extrapolate it to what will execute in parallel when you run it on a 100-core machine. And this is what the series parallel relationship has to capture. And this is where the challenge lies. And then once you have this data structure, you do fine-grained measurements. And this is what our performance model is. So in the context of OpenMP, we have a new logical series parallel relationship, which we call OpenMP series parallel graph. And OpenMP is interesting primarily because it captures both threading and tasking. What is threading? Like you execute a bunch of threads and do something with it. And tasking is you create a bunch of tasks and rely on the runtime to map them to underlying threads. So this combination of threading and tasking creates interesting challenges. So our series parallel graph is something similar to DPST, which Martin was involved with some time earlier. So I'm going to describe like how this OSPG is constructed so that you have an idea of what logical parallelism, what are the things that are required to compute logical parallelism. So let me start by giving you a simple example of what OpenMP parallelization or parallelizing code with OpenMP looks like. This is a simple code snippet. For simplicity, let's assume ABC are simple C functions without any parallelism calls internally. So how do you parallelize your C++ code? If you want B to be executed in parallel by a couple of threads, we just add this pragma, which is OpenMP directive, telling it pragma OpenMP parallel. What does OpenMP do? It creates a team of threads and executes the code, the block following the pragma in parallel. So this would be the execution structure. A gets executed, and then you have a team of threads that are created. They both execute B, and then there's an implicit barrier at the end of this pragma, and then C executes in series. Okay? So this is the execution structure. Like you may have such structures as you execute. Now we want to construct a graph that precisely captures which fragments of this execute in series, which fragments execute in parallel. Okay? So to do this, one thing to note is all the interesting computation in this code happens in A, B, and C. And A, B, and C are functions without any further OpenMP directives, right? So all the computation are represented in our OpenMP series parallel graph with W nodes. These are the work nodes. So what is a work node? It's a dynamic sequence of instructions between two OpenMP directives. Okay? And all interesting computation happen in these work nodes. And now some fraction of these work nodes actually execute in series, some fraction execute in parallel. When you execute it on an ideal machine, which is infinite cores and with an ideal runtime, right? Now you need to construct a tree that captures the series parallel relationship. To capture the series parallel relationship, we introduce two kinds of nodes. P nodes. What is the property of a P node? The subtree under the P node executes in parallel with anything to the right of the P node. Okay? So in this case, the subtree under the P node, W2, would execute in parallel with any nodes to the right and their siblings. Okay? So this is the property of a P node. And these capture like asynchronous execution of parallel tasks. And then we have another kind of nodes, what we call as S nodes, series nodes. These capture the property, the subtree under the S node, execute in series with anything to the right of the S node. Okay? So this captures a sync block. You have a sequence of parallel calls followed by a sync or a barrier. In the Silk terminology, it's a sync, or in the OpenMP world, it's a barrier. Okay? So now this is the data structure, the tree representation of the data structure that we are using to measure logical series parallel relationships. So you execute this on a single core machine with a team of 2 threads, you'll have the same series parallel graph. So now, how do you identify whether two work nodes execute in series or parallel? You compute the least common ancestor. In this case, the least common ancestor is S2, and you find the left child of the least common ancestor. If it happens to be a P node, and then the 2 nodes execute in parallel, logically executes in parallel. And similarly, if you want to check whether 2 nodes execute in series, compute the least common ancestor. If it happens to be if the left child happens to be a S node, then those 2 execute in series. Going back to the slide, W2 and W3, which corresponds to this B2 and B3, which is parallel execution, they execute in parallel because the least common ancestor is S2, and the left child is at P1, which is a P node. And in another example, looking at W2 and W4, these are 2 work nodes. They execute in series because the least common ancestor is a S1 and its left child is a S2. Okay, so by doing simple LCA queries, we can identify whether 2 nodes execute in parallel, logically execute in parallel, or logically execute in series. So what is the takeaway? There's a lot of jargon, right? So the takeaway here is, during the execution, we are going to construct this data structure, okay, which captures what fragments of your execution logically execute in series and logically execute in parallel. Okay? So what is the profiler going to do? It's going to construct this data structure as the program executes. And then we are going to do some measurements to compute parallelism and what matters for your entire program's performance. Okay, so let me walk you through. This was like just a pedantic example, right? Like now let me take a concrete program and walk you through, like how does the code look like? This is the program that I'm going to work with. Like it's a small program, but I'm going to walk you through. This is a simple merge sort that I would teach in a parallel programming class. Very ideal for recursive decomposition style parallelism, right? What do I have? So what do I have? Like I have a main program. I'm initializing an array of like some numbers, like and the entire program has to terminate. So I have at the end, right? So I have a S node to indicate the entire program terminates at the beginning, after it completes. So then there is some work that is done by the program before you encounter an OpenMP directive. This is captured with a W node. So this is the work that is done before you encounter the first directive. Okay? And then you encounter the first pragma call. You have an OpenMP directive. It's saying, I'm going to create a team of threads, and I'm going to execute whatever code that follows it in parallel, the entire block that follows it in parallel. And in this case, I'm assuming you have 2 threads, and you're executing them in parallel. So OpenMP also has a barrier at the end of a parallel section. So what does a barrier mean? You have a team of threads that are terminating in a barrier. So we have a S node to indicate there's a sync block, and then you have a team of 2 threads. In this case, you're executing on a machine with 2 cores. You have a team of 2 threads, and they're going to execute some code. And within the OpenMP parallel region, you have a pragma single call. That is, you want only 1 thread in the team to execute the code following the single call, single pragma. So So thread P1 in this case, it does not, let's say P0 executes this a merge sort call, the other thread just goes and reaches the barrier. So it does a small amount of work, it's done. Okay, the P0 starts executing the merge sort function. Okay? And what is the first thing in merge sort? You have now P0 is executing this merge sort function, so it's doing some work. So we created a W node, which captures this check whether the bound is less than some cutoff. Like when you do merge sort, like you recursively split until you hit a base case, right? When you hit a base case, you just sort it serially, because sorting anything recursively for numbers numbers less than 100 elements is expensive. So this is captured by this node W2, and then subsequently you encountered another pragma which creates a task. You're creating a new task with a pragma OMP task. So the key thing to take away here is like creating tasks is pretty simple. Like you just need to add these pragmas. Now you have a task. Like this part is executed as a separate task. And what is the program doing? It's creating a task for the left part to merge the left part, creating a task to merge the right part, and then you have a task wait. It waits for both the tasks to complete, and then you have a merge. This is merge sort in a nutshell, right? So now you have a series of tasks followed by a task wait. So this is a sync block. So you create a S node, and you create two P nodes because you have two tasks. And these tasks, when they execute, they would do some work within them. So those would be executing the serial sort. Okay? And once these two tasks complete, this entire sync block is completed. So this entire subtree is completed. So the final merge happens as a child of as the work done by the initial member of the team. Okay. So again, if you got lost, it's okay. The thing I want you to take away is during the execution, we are constructing this series parallel relationship. So how the series parallel relationship is very close to tied to the semantics of the directives that you have. Okay? And once you have this graph, now you can identify what parts execute in series, what part executes in parallel. Okay? So for more details, and if you want to know more about the details of the OSPG, come talk to me. And if you want to, this is similar to DPST that was proposed by Raghavan Raman along with Martin and others. But the key difference is it models the semantics of OpenMP directives much more carefully. You don't have an explicit finish or explicit async in the case of OpenMP. Okay, so what have we accomplished? We have taken a program, we have constructed the logical series parallel relationship. And now is the interesting profiling part. You want to compute logical parallelism. What do? So all the work is happening in these W nodes, right? You measure what is the work performed by these nodes. And how do we do this in a modern system? We use hardware performance counters. It is lightweight, non-intrusive way of measuring how much computation is performed. So we use hardware performance counters to measure work performed by each of the fragments. And now this is what we call as the performance model, this logical series parallel relationship with fine-grained measurement in these work nodes. Okay? So you can't maintain this entire series parallel relationship in memory because like if you have a very large program, this graph is going to be humongous. Our profiler does not maintain it in memory. It just maintains a small fraction that is required to compute logical series, the parallelism computation. Okay, so now you have the series parallel relationship. Now you want to compute what is the total parallelism. Wow, what is the parallelism? You give it infinite number of machines, an ideal runtime, how much speed up am I going to get? Okay, what do I have? I have work performed in the leaf nodes. You want to compute the work performed in the intermediate nodes. Okay, so if you have a subtree, what is the total work done by the subtree? It's a sum of all the work done by the intermediate nodes in the subtree, all the W nodes in the subtree. You just compute it for each internal node. So P2, there's only one W node in the subtree, so you compute the work done by P2 is just 100. And similarly, you have P0, there are like W0, W2, W3, and W4. These are the work nodes in the subtree, sum of their work, that is the total work done by by this subtree. And similarly, compute it for the entire node. So what does this say? This is the total work performed by this entire program. So if you took the entire program, just ran performance counters out of the blue, you would get this work. This is not a big deal. Like, you don't even have to construct this logical series parallel relationship to measure the total work in the program. Just run perf and run the program, you get the total work. But what we need to do to compute logical parallelism is what part of this work, there are all these W nodes. In this case, there's a set of W nodes, W0, W1, W2, W3, W4, W5, and so on, right? What subset of these nodes have to execute serially? So this is the interesting part. Like, why are we doing all these fine-grained measurements? Why are we doing all this logical series parallel relation? Why are we computing this graph? Is to measure what subset of these W nodes have to execute serially. Not in a given execution, but in an ideal execution. So we have to compute what subset of these nodes execute serially. So you have a subtree, and there are a set of work nodes within the subtree. A small subset of them will execute serially, according to the semantics of the program execution. And we have to compute the subset that performs the maximum amount of work. That is your critical path under the subtree. And we have to do this for the entire program, incremental. Okay? So let's start here. P2 has only one child. So, and this has to execute serially. So the P2 serial work is just this. And you have S2 here. S2 has two children, P2 and P3. And these are P nodes, so both of them execute in parallel. So the serial work is either the work of W2 or the work of W3. So these are the base cases, which are easy to compute. Now we are at node P0. So what are the work nodes under P0? W1, W2, W3, W4. These are the total set of work nodes. Out of this, only a small fraction of them have to execute serially. W1 has to execute serially. W1, W2, W4 have to execute serially. And similarly, W1, W3, and W4 has to execute serially. And if you just do the LCA for all these nodes, it'll appear that they have to execute serially. So now you need to compute what is the work done by each of these subsets of work nodes that have to execute serially. And recompute it for the entire graph. So you do this for P2, it's just exactly the nodes. S2 is max of whatever work in W2, whatever work in W3. And the work for P0 is max of W1, W2, and W4, which is 2 plus 100 plus 52. This is 154. And S1 is just one node, so it's just 154. And finally, the serial work for S0 is W0 plus whatever the serial work of this, 156 plus 6, which is 160. So what have we calculated till now? The total work in the program is 260 units of work, and you have to do 160 units of this work serially. And this is in an ideal execution. So what does it say? Even if I give you infinite number of machines and an ideal execution environment, this program is going to have W260 divided by 160 is the maximum speedup that you are going to get. This program has very low parallelism. So this performance model plus fine-grained measurement has a lot of information. You can give it to the user. But programmers care about their code, right? They don't want to see about all the notational fiction that we design. Okay? So what do we do? We summarize it to actual directives. For each directive, we provide what is the parallelism for that is attributed to a particular directive, and what fraction of the work has to execute serially. And what does it look like? It looks like your entire program has this units of work. This is the serial work. This is the parallelism. And this is the percentage of work that is done exclusively, that is on the critical path, that is exclusively performed by this particular sponsor. So this is the profiler part of our tool. So essentially, what are we doing? You take a program, and you're measuring logical parallelism. And you're saying these are the serialization bottlenecks in your code. And this is similar to some of the other work that Martin was alluding to. Like SilkProf would compute, but since we explicitly keep track of the logical series parallel relationship, we are much, much more accurate than what SilkProf computes. Because otherwise, they would have to do some additional work for recursion and other things. So, but the interesting part comes in with the advisor mode. So what do we want to do is, we want to estimate what are the things that the programmers have to address to increase parallelism. So we have to estimate speed up. And this is where you need a performance model, right? Even before you parallelize, what matters in increasing logical parallelism. And this is what we call as our what-if analysis. Our what-if analysis mimic the effect of parallelization with our performance model and estimate what is the increase in logical parallelism. Okay? So now you have this performance model. What are the regions that you should focus on? What regions should you select? So one obvious choice would be I select the node on the critical path that is performing the highest amount of serial work. Critical path is restricting the parallelism. So select the node that performs the highest amount of work on the critical path. So this was the critical path for your entire program, W0, W1, W2, W4, and W2 happens to be the node that performs the highest amount of work on the critical path. Choose this. Okay? So, and then this is the dynamic instance of a static region of code. What do we do? So we identify, this is the dynamic instance, identify the corresponding source code region that corresponds to this W node. And then we identify all dynamic instances of the same region. So what happens when you parallelize? Like you parallelize a certain region of code. Wherever this region actually manifests in the execution, those will get accelerated if you parallelize it. So we identify what is the static region of code that corresponds to W2. In this case, it happens to be W2 and W3. And in this case, we mimic the act of parallelization. So let's say we are parallelizing this region of code by 4x. We are using SIMD operations there so that the parallelism is going to increase by 4x. So what happens when you parallelize it? So the total work remains the same, but the serial work rate gets reduced by the parallelization factor. Okay? So your total work was 100, like you parallelize it by 4x, then now the serial work is 25. You recompute the entire parallelism. And you produce a what-if profile. If you hypothetically optimize this region, this is the parallelism in the program. And as you can see, the parallelism has now increased to 3.05 or 3x. So this has progressed from 1.6 to 3x. So this is something that may be beneficial. And you repeat this entire process until you reach a threshold for your parallelism. Like let's say you want to run it on a 128 core machine, you want the parallelism to be much higher than 128, right? So you keep repeating this procedure. Okay? So this is what-if analysis. What are the things to take away? We want to measure logical parallelism. To measure logical parallelism, we constructed this performance model, which is series parallel relationship with fine-grained measurements. And once you have this, what does our what-if analysis do? It mimics the act of parallelization. What happens when you parallelize code? You do the same amount of work, but you reduce the amount of work that you do serially. Okay? And you can compute the logical parallelism again. Ideally, what would you do? Like you would make every region do 0 amounts of work, right? You have infinite parallelism. World is very nice, right? This is like some hypothetical model that I'm building, right? But real world is much more complicated. So when you increase parallelism, there's a cost that you need to pay. What is the cost that you need to pay? There's a cost to orchestrate parallelism. Using SIMD instructions is not cheap. Using threads is not cheap. Using tasks incurs some cost. So how does this cost get manifested? So your runtime overhead increases. So there's a delicate interplay between parallelism and runtime overhead. Okay? So you need to keep that into account. If you have high runtime overhead, even if you have a lot of parallelism, you're going to have low speed up. So you need to take the cost of orchestrating parallelism into account. How does it get manifested in our what-if analysis? When you mimic the act of parallelization, so you take the cost of parallelism into account. Okay? So what is the minimum amount of work that you need to do? You have to do at least the work that you incur to create tasks or create parallel execution, or the work divided by the parallelization that you are going to do. Okay? And you repeat this entire process until you cannot parallelize a region anymore. So, or you reach the work of each node has already exceeded the cost of parallel execution already exceeded the amount of parallelism that you can the benefits that you can obtain from parallelism. So the key thing is like you have to have benefits from parallel execution. The amount of work that you need to perform in a single parallel node has to be sufficiently large than the cost to create tasks or cost to create parallel execution. Okay, so just to recap, what is happening? So you have an OpenMP program. You run the profiler. You get the series parallel relationship, and it performs some fine-grained measurements. And it produces a parallelism profile, which tells you what are the serialization regions, and what are the regions that you need to optimize to increase the parallelism to some threshold that you want. And if you do that, what would be the profile? What would the profile look like? Okay? So this is increasing your ideal world parallelism. The last thing that you need to address is you have a lot of parallelism, but you still don't get speed up. Okay? So why can it happen? You have secondary effects. What are secondary effects? You're running you're running a parallel program, and you have a lot of cache misses, and the cache misses are going to reduce the speed up. Okay? So what do? And you want to carefully measure them. And how do you do this? So we use the same procedure. What my student discovered was like, he had this clever insight. Construct this performance model. And when you have secondary effects, you're going to have inflation in some metric. Ideally, there will be some, you'll be doing a lot more work than compared to an ideal execution. You're incurring cache misses. Like caches are like oblivious to program from an ISA perspective, but like you can see it in the performance profile. Okay? So if your program is experiencing a lot of cache misses, you are going to do a lot more work in the entire program and in a specific region. Now you construct, like let's say, you construct a performance model for the Oracle execution and a performance model for the parallel execution. Okay? Assuming this is a deterministic program, there are no races, these performance models will look identical. Okay? And what happens due to secondary effects? There will be inflation in this work. So for example, this W node is performing 100 units of work, but in the parallel execution, it's doing like 200 units of work. Okay? Or 185 units of work. So there is work inflation. And now, just summarize it to the user. And what my student discovered was that you can do this for multiple metrics of interest. Like modern hardware has like a gazillion number of counters which you can use. Repeat this entire process and run it with a lot of metrics. For example, there's a counter called hitm, which says number of accesses to your cache in the modified state. Why do you have accesses to the cache in the modified state if you have true sharing or false sharing? And then you present a profile, which we call as a differential profile like this. So for each region of your program, what is the inflation in work that you're seeing? And what is the inflation in various other counters? So this program is seeing 4x inflation in work, and 13x inflation in hitm counters, and some inflation in remote DRAM accesses. So this and then if you look at like region 2 to 4, it's seeing like almost 18x inflation in hitm counters. So this program has a lot of data sharing issues. So it either has true or false sharing, which is causing the performance to go down. So this is correlation is not causation, but this can highlight, this localizes the problem to a region of code that the developer can look at subsequently. So this is what we call as differential analysis. Okay, so we have a prototype which is available for multiple, for OpenMP programs, Intel TBB programs, and you take an OpenMP program. What do? We use the callbacks that is present in LLVM, and we have our own OpenMP library that constructs the series parallel relationship. You create a binary, it runs, it creates the parallelism profile, tells you what are the regions that you need to optimize, and what the resultant parallelism would be, and what the differential profile look like, if there is any inflation. How much time do I have? Okay, so like it's over. Like I'm just giving you a quick snippet of what my student discovered. Like he was parallelizing a program. He was performance debugging a program called MIL-CMK, and the initial parallelism profile was something like this. It had 44x parallelism, but it had 2x speed up on a 8-core machine. And he used the what-if analysis. It told these are the regions that you need to focus on. And again, this is some C code and lines 81 to 91. And if you do that, your parallelism would increase to 90. And these are the regions of code that actually were highlighted by the what if regions. And if you look at it, like it's doing a for loop, some sort of a reduction. And what my student did was he just replaced it with parallel reduce. Okay? And this code had about 6,000 lines of code, and he didn't even write it. This is someone like that was given to him. And he replaced it with parallel reduce. And this increased the speed up a bit, like from 2x to 4x. And then he used the differential profile, and he saw, oh, there was 3x inflation in work, and there was a lot of inflation in remote DRAM accesses. And why do you see remote DRAM accesses? Like you are doing parallel execution, and someone is producing the data, and other thread, other task is accessing the data. So this indicated a problem with affinity, and what he did was he changed the affinity partitioner that was being used, and that increased the speed up to 6x on an 8-core machine. So this demonstrates, at least to me, the usefulness of providing concrete evidence to the programmer. Okay, so we found this tool pretty effective in diagnosing a lot of performance bugs. So we are currently in talks with the Intel vTune Tube so that they can integrate it with the Thread Advisor. So my student is joining Intel. Hopefully this transition happens. That's the hope. So if you're teaching parallelism courses, the entire code base is available open source. Use it and give us feedback. We're constantly improving it. And to summarize, like, there is a value in measuring logical parallelism using the logical series parallel relationship plus fine-grained measurements is a useful abstraction to reason about both logical parallelism and also do a lot of other cool things with, such as differential analysis. And if there is one thing I want you to take away from the talk, rather than just telling where the code is spending its time, it will be useful if you tell what matters to the programmer, like whatever metric the programmer is interested in. And finally, like I just advertise the work done by my students. My students do a lot of cool work. There's a lot of other interesting projects. Martin mentioned Alive, which is the compiler verification work, but we also have some cool work on crypto verification. We call it Chasm Verify. How do you do automated equivalence checking for crypto code? We have some really cool work going on new abstraction that can potentially replace floating point. We in collaboration with John Gustafsson, who proposed posits. So if you're interested, talk to me. Since I'm out of time and I'm standing between you and lunch, I'll stop here. Okay, thank you for your attention.
Okay, any questions? No questions? So I have a question on your like first example, like this. So once the program is in a task parallel form, so you can see where the bottleneck is, but like for some problems like sequence processing, like computing some property, like a prefix sums or something, then the programmer may not even have put it in a task parallel form, and then it's like what happens?
So typically, what is a parallel reduce? Like you're doing a parallel scan, right? So underneath the high-level abstraction, internally you're using some parallel stream of execution to model it. So what we do is we don't just capture the high-level abstraction. We capture the underneath, like what is the actual sequence of threads that are being generated and what are the fragments that are being run in parallel, and we can measure it. Like you can tell, like, oh, this is the parallel scan part, which is incurring a lot of overhead.
But I'm saying that it may not even be written in this way. Like if you're processing a sequence where it's like looks linear, but actually you can process it in a not linear complexity. So you might have to like redesign the program in a completely different way.
Sure. So again, our goal is like we're not designing new algorithms, right? Like we're not estimating what is the benefit that you would get if you design it with a new algorithm. Given the same algorithm, will a better reorganization of the parallelism structures give you a better performance?
Okay, good question there. Oh, yeah.
Santosh, very interesting work. Just wonder, how do I trust the numbers that you produce?
So one thing you can validate is like you run the program just without anything with a profiler, just with regular perf. You can get the work, and if it matches whatever we are doing, it's again like you either have to instrument manually or like write micro benchmarks to test it. So the question is, Yeah, I produced a bunch of numbers, right? What do they mean? Like, how are they even correct, right? So that's an interesting question. So the way we validate our answers is we write a lot of micro benchmarks and we isolate each parts of them. And after making any change, we run regression so that all our results are valid. So there is some ground truth that has to be maintained. And as developers of this profiler and advisor, we have developed a repo of all these micro benchmarks that have the ground truth. Jim? Oh, okay. We'll take Jim and then yours.
Does your tool take into account the size of the input and the speed up you get for different size inputs?
For the entire profiling is done for a given input. It's an execution for a given input, but the regions that we report are typically like for all the speedups. For the mil-CMK example, my student parallelized this region of code. He ran it with it was reported for a single input. When he ran it with multiple other inputs, they also showed improved speedups. So, but this is all the information that is given by the profiler is for a specific execution for a specific input. So what is independent is it's independent of the schedule. Or independent, like the threads are not part of the input.
Yeah, so my question was in fact very similar. I guess you're assuming that your program behavior or the profiling is quite uniform above different inputs. So what if that is not the case? So if you really have different behaviors for different inputs, would you then just repeat the process for different inputs, or is there a better strategy? So
what we do is, if you have multiple sets of inputs, we generate profiles for each of them and reconcile the summary that we get. So the way we generate the parallelism profile for each inputs and the what-if analysis regions for each of the inputs. And then whatever we report to the programmer is whatever provides you, what are the regions that uniformly provide you across all inputs.
Okay, but then it can, I guess, depend on the order in which you are using your inputs, what kind of recommendations you get. Yeah.
So again, that's a hard problem, right? So how do you reconcile input into your parallelism structure? So what we are doing is a best effort guidance to the programmer. And this is not a definitive word in the sense we are not assuring, we are saying for this input, if you parallelize this, you'll get speed up. It may not work for other inputs.
I had a quick question actually on speaking of these inputs, can you imagine doing a symbolic task parallel graph? Because then you have then you compute the symbolic representation and just ask the question on the input, give me the input which actually has the most disbalance.
It's doable, but how do you scale it in a fashion that is meaningful for large programs? I don't have a solution right now for it.
Okay, so let's thank Santosh again.